Hey everybody, welcome to Coulomb's Law. Basically what I'm going to try to do is give you an idea of how to look at this first from the sort of the theoretical side and then work it into the number crunching part. And we're going to have to be really careful about the number crunching part because it's very easy to confuse the idea of the scalar nature of charge, doesn't have direction, with the vector nature of force. And there's some mistakes that often students make when they're going through this. So just to give you the background for starters, this whole Coulomb's law thing is named after a guy named Charles Augustin de Coulomb. And that's my attempt to try to sound like I know how to speak French. You can see from the clothing he's wearing here, he doesn't look like your typical scientist at all. And that's because he was actually in the French military. He was born to a very rich, wealthy family in Angoulême, France. And he very much went kind of against family wishes, against the grain, sort of, because he said, I'm really interested in science and I want to be in the military. And he found a way to do both of those because he entered the French military college called the École du Génie, which still exists to this day, and basically got them to pay for his entire education, essentially being what we would today think of as being an engineer. And definitely with sort of a science spin to it as well. It was while he was stationed in Paris that he started to work on a whole bunch of his own sort of side science projects. Now, it does lead to a little bit of weirdness for him because you'll note here that I'm saying he published 7 memoirs, 7 papers. This is different from what most scientists will do because a scientist will come up with their research, they'll write it up essentially as a fancy lab report, and then they'll get it published in a scientific journal. Coulomb couldn't do that. He wasn't a professor at a university, so he wasn't allowed to do that, basically. So that's why we refer to his work as memoirs. Memoirs sometimes means almost like an autobiography for a person. For him here, it's self-published scientific papers. It didn't hold him back, though, because the work he was doing was actually really awesome, and he became extremely famous in scientific circles for this. The main one that we're focusing on, one particular study he did, was involving the inverse square law of forces between two charged particles. Now, if that idea, inverse square law of forces, kind of sounds familiar, it's even going to seem more familiar to you when I mention the torsion balance experiment. You might remember this from Physics 20 when we were talking about Henry Cavendish and how he did an experiment to measure big G, the universal constant, the number that Sir Isaac Newton himself couldn't get, and it's what held him back from using his own formula, Fg equals gmm over r squared. Now, right there, the r squared part, that's the inverse square law thing that we did back in Physics 20. This idea that if you have two masses, they will attract each other because of the force of gravity acting between them. But if you increase the distance between them, exponentially the force decreases. Now, the reason I mention that is because we're going to see that the inverse square law that Coulomb comes up with is practically identical. Like the structure of it is really the same. And when I show you this experiment, you should go, hey, yeah, that's Cavendish's thing. No, it isn't. It's actually Coulomb's thing. Coulomb came up with the torsion balance experiment, and he did it with these objects having positive and negative charges on them. It was when Cavendish read about this experiment that he said, hey, I can take that, I can change it, and use it just as masses without the charges and measure stuff about universal law of gravitation. So when we have Coulomb come along and do his experiment, um, he does have these 2 red metal spheres attached to the end of the rod, hanging from a wire. And this is like us doing a top-down view, like we're on the ceiling looking down on it. So the wire is coming out of the page towards us. Um, The other two metal spheres that he's got, one here and one down here, they're positively charged. The ones that I've got colored in blue here that are the positive charges, they're anchored down. They can't move at all. So that when he releases this whole thing on its own, oh, sorry, I gotta get back to where I can actually click things here. The whole part that's hanging from the wire rotates because this red negative sphere wants to be near the blue positive sphere, and the same thing on the other side as well. Um, with it kind of set up this way, um, it does kind of look like we're talking about, four objects. Obviously, we are, but we treat the two red balls as being together one negative charged object, and the two blue objects, again, as being one positively charged object. The big deal here, though, is the whole thing has rotated because of the electrostatic force attracting the charged objects to each other. This whole thing spins until the twisting of the wire is so much that the torque exactly balances back against Fe. You see, just like when Cavendish was doing his experiment, Coulomb has no way of measuring Fe directly, but he knows when it gets to this position and then stops moving, the torque from the wire twisting back against it is exactly equal but balanced out by Fe that pushed it that far. We've got a situation of F net equals zero, but we know then that if it takes a certain amount of torque to twist the wire this much, that's something that's measurable, then we actually indirectly know what Fe is. Now from this, Coulomb comes up with his formula. And this is why I wanted to point out that other formula to you first, because doesn't this look like universal law of gravitation? It's just that instead of Fg, we have Fe. Instead of big G, a gravitational constant, we have little k, which is known as Coulomb's constant. We have Q1 and Q2. Those are the charges on the two objects instead of masses. And notice also that the units, the units that we measure charge in are coulombs of charge. So it's Coulomb's law with little k Coulomb's constant and measuring charges in coulombs. I guess, if you discover something, you can name everything after yourself, right? And then on the bottom, it is still an inverse square law because we're still looking at r squared, the distance between the centers. Just like in physics 20, we're using r to make us think of the word radius, because that's when we measure to the center of something. So this is measured center to center distances squared. So it's still an inverse square law. By the way, little k Coulomb's constant is on your data sheet. And again, it's like big G was a universal constant, little k is a universal constant. And it's got really ugly units because they basically just, everything has to cancel out on this side so that we get newtons on the left. Now, when we're talking about measuring little q, the amount of charge of something, we've got a huge range of numbers that can happen in physics. If we're talking about like individual electrons and protons, their charges come in at negative 1.60 times 10 to negative 19 coulombs and positive 1.60 times 10 to negative 19 coulombs. Because remember, electrons and protons, same amount of charge, just opposite sign. We can go up to something like lightning bolts. And I use that example because it is very definitely an example of static charges discharging. 2 to 3 coulombs in a lightning bolt. Now, what this should make you think of is when you're talking about individual charges like an electron, yeah, you're talking about really small numbers. But when you're talking about a lot of charge, like a lightning bolt, the numbers actually aren't that big. They're very normal looking numbers, like 2 or 3. To get charges into the like 10 to the positive 2 range or something like that even, that's actually pretty difficult. It's actually hard to get a lot of charge concentrated in one area without it trying to discharge itself. On your data sheet, you're not going to see them list an electron as being that charge. Instead, if you look in the top right of the data sheet where all the constants are, you'll see that an electron is listed as negative 1e. That's because on your data sheet, on the left-hand side, it says elementary charge, E for elementary, not electron, is equal to 1.60 times 10 to the negative 19 coulombs. This is seen as being the most basic charge possible because it is the smallest charge possible. You get down to a single electron, that's the smallest negative charge you can have, and a single proton, the single smallest possible positive charge you can have. So we do everything in terms of elementary charge. That's why when you look at a proton on the right-hand side of the data sheet, it says positive 1e, and a neutron is 0. There is something listed there called an alpha particle, and it says negative 2e. That's because it's a double elementary charge. You would take this number and multiply it by 2. Now I am asking this question, so how many electrons are in negative 1 Coulomb of charge? Like, how much is that? I'm just going to try to move something out of the way here. There we go. So what I would have to do is actually set up sort of like a ratio for myself. And in that ratio, it would look something like this. 1 Coulomb of charge, because that's what I'm asking about. Don't even worry about the negative sign here. I set up my ratio as 1 electron is 1.60 times 10 to the negative 19 coulombs, so that the coulombs on the top, coulombs on the bottom, coulomb per coulomb, that's 1, it cancels. It's going to give me an answer in electrons. So I'm really taking 1 divided by the charge on 1 electron. And I get this insanely huge number, 6.25 times 10 to the 18 electrons. That's a lot of electrons. And that's partly why it's very difficult to get like even a Coulomb of negative charge, because it would be that many electrons alone, not like in a pencil that you're holding where there are huge numbers of electrons like that, but there's the same number of protons also. And so they cancel out each other's charge. I try to get that many electrons alone, super difficult. Just not something that's easy to really get to have happen. So I've got this example for you where I say, how much force would be exerted then between two objects that I've got with charge held apart by some sort of distance? So I'm telling you that I've got a comb and it's got a charge of negative 2.0. That weird symbol is micro. It's on the data sheet. We're going to have to take care of that. Negative 2.0 microcoulombs. And apparently a person's hair fell out while they were combing their hair. The hair has a charge of positive 3 microcoulombs. Right now, the distance between them is 0.15 meters, and that distance, because it doesn't say anything more specific, has to be measured center to center. We have to assume that unless they say anything different. So I grab my formula here, and I start substituting in the numbers. I got to be careful because remember, microcoulombs, I can't just leave it that way. I have to change it to 2.0 times 10 to the negative 6. Just like the 3 microcoulombs becomes 3.0 times 10 to the negative 6. Now I'm hoping you're even just looking at this stuff on the top and you say, well, what happened to the negative sign on the charge of the comb? This is something we have to be really careful about when we're using Coulomb's law. It's also why when you even look at it on the data sheet, Fe has absolute value bars around it. We don't want to talk about positives and negatives from putting signs on here because those are signs based on charge, that's scalar. If I start saying, oh, that's why I have a negative sign over here on my force, that means something really specific in physics. That means to like the left or down. We avoid that. All that we do is we put in absolute values for the charge, and then later we'll decide something about the direction of the force based on law of charges. Opposites attract like repel. Finally, down here on the bottom, 0.15 meters, don't forget to square it. I get my answer. comes out as 2.4 newtons of force. So what do I say if I'm talking about the force the hair exerts on the comb? They are opposite charges, and since the hair is to the right of the comb, there's going to be attraction. The hair will pull the comb to the right because it's going to attract it. If I flip this question around and I said, what does the comb do to the hair? I have to focus on the comb in my diagram being on the left-hand side. It's still going to do attraction because opposites attract. The comb will pull the hair to the left. It's the same amount of force either way. The comb pulls on the hair with 2.4 newtons. The hair pulls on the comb with 2.4 newtons. They both do the same amount of force, Newton's third law, but in opposite directions to each other. And I just calculate it using Coulomb's law. Moving right along, what about when we have multiple charges arranged in a 1D question? So I've got all these charges in a straight line. And even though there's 3 of them, I can't just change my Coulomb's law formula to have 3 charges. I can only do 2 charges at a time in the formula. So we actually do this the way that we would have done multiple masses with universal law of gravitation back in physics 20. I ignore one of the charges. Well, for a little while at least. I'm not saying that I'm getting rid of it entirely, but since I want to know what's the force acting on charge 3, I'm going to first figure out what's charge 1 doing to charge 3. I know the charge on both of these charges. I know the total distance, because this is the distance separating them compared to where Q2 is in the middle here. So I'm just going to take these 2 distances and add them to find the total distance center to center between them. So I set up Coulomb's law, Coulomb's constant, the charge on Q1, the charge on Q2, and the total distance separating them squared. And I get this number. Now I'm already thinking kind of in the back of my head. Q1 is positive, Q3 is negative. So when I look at, hey, what's happening to Q3? I say to myself, well, Q3 is negative. It would be attracted towards Q1. So that means Q3 feels itself being pulled to the left. Now, if you want to interpret that as, just even writing to the left, sorry, this is really sloppy for that, or if instead you want to think of it as a negative sign on it, you can say that at this point, when you finish the calculation and you're trying to figure out something about directions and stuff. I haven't rounded this number, by the way, yet, because I'm not done yet. I've still got to do other stuff. But this number right now is the amount of force that Q3 feels from Q1 attracting it, pulling it towards the left. Now remember, I said I'm not getting rid of Q2 forever. Now I'm going to do Q2 with Q3. I need to know what Q2 does to Q3. I know the charge on each of them, and I know how far apart they are. So I set up Coulomb's law, Coulomb's constant, charge on Q2, charge on Q3, and notice all the way through this, nothing about the sign on the charges. And they are 1.7 meters apart, so 1.7 squared on the bottom. I go through all the number crunchies, I get an answer. Now I'm looking at, so what's happening to Q3 because of Q2? They're both negative, so they're going to be repelling. That means Q3 feels itself being pushed away to the right. So this force is positive. It's to the right. The first force was to the left. This force is to the right. I'm going to keep that in mind. Now, do I have to do another calculation where, and I'm just going to jump this back for a second, where I have to calculate the force between Q1 and Q2? Sorry, no, I don't have to do that. because I don't care what they're doing to each other. The question said, what is the overall force acting on Q3? So I only have to be concerned about combinations of forces that involve the third charge. Anyways, I've got the first force that we calculated, which I'm saying is negative because it was to the left. The second charge that we, or the second force that we calculated, which is positive because it's to the right. I add them together. Now I round off for sig digs, looking at all my original numbers and stuff. And I say, yeah, because it's positive, that's a force pushing to the right. The Q3 feels a net force, because of everything that's happening to it, of 0.20 newtons to the right. So what about multiple charges in 2D? This is where it can kind of get ugly, right? Because now we don't have everything lined up in a straight line, left to right, and that's it. I've got a two-dimensional situation. I've got angles and stuff. So here's a few things I can tell you about these sorts of questions. Most often, you're going to see them drawn as right-angle triangles like this one, because there is a line that connects Q1 to Q3 that would be the hypotenuse. And when they do that, probably they're going to ask you about the charge that's in the corner opposite the hypotenuse. That way, anything that's happening between Q1 and Q2, like in this diagram, is going to be a vertical component, a y component, and nothing else. And anything that's happening between Q2 and Q3 is going to be a horizontal x component and nothing else. That means that I'm going to figure out the net force on this based on a y component and a x component. Now, if they don't do that, it does mean, like if you're trying to do things for Q3, you'd have to start breaking up components and stuff like that. I think, though, if you're going to see a question like that, it's more likely probably going to be that the three charges are arranged in an equilateral triangle where all the sides are equal and all the angles are 60 degrees, or an isosceles triangle. Now, there's some like that that are in the homework in the textbook, and I want you to honestly give those a try first before I say, oh yeah, do this, do that, because it really is all just vectors and vector analysis. Anyways, if I was doing this one and I wanted to know what's the net force on Q2, I do the force between Q1 and Q2. I have the two charges and the distance. I could use Coulomb's law. And, oh, sorry, apparently I did these two forces first between Q2 and Q3. Sorry, I thought I had the other one done first. I know the two charges. I know the distance between them. I put it in Coulomb's law, and I get this much force, which you'll notice is enormous because both of these charges are enormous. When would I ever get charges of 4 coulombs and 1 coulomb on two separate objects 4 meters apart? They discharge. They do crazy things. Anyways, this is all theoretical. So I get this much force, and it's going to push this one, Q2, the red one, to the left because they're both positive charges. They're going to repel. The red one will feel itself being pushed away from the green one. The blue one, Q1, now I'll do its calculation. It's going to push the red one also away. It's going to push it downwards because, again, they're both positive. What I would now do is take one of these vectors and move it so that I can get them to add head to tail, and then draw in my resultant, do some Pythagoras to get the force, figure out the angle that's near the tail of my resultant, use some trig, and I get an answer that looks like that. I'm leaving this for you to kind of double check, try on your own to see if you could get through it, but those are all the numbers that we would get. Now, I fully expect that you're going to want to probably look back at some of this stuff. You could look at the slideshow on its own. I'm going to post up this video in the Google Classroom so that you can watch it there also. But at the end of the day, you are going to have to, try working through some of these yourself also. For the homework, I've got some stuff that is very 1D-ish, that is the basic straight line sort of stuff, a little bit of 2D stuff, and because technically this does bring us to the end of the chapter now, even some questions from the review at the end of the chapter. So a little bit of everything, not just Coulomb's law stuff. Good luck with that.